So I'm gonna tell you a crazy but true story about the nature of your universe. So you may have heard this word quantum computing. It's often people have the misconception that it's some kind of newfangled supercomputer. It's decidedly not that. Quantum computers allow us to access hidden features of nature, new dimensions, and if we can access these sort of hidden dimensions at scale, we could have unimaginable computing power. To put it in context, throughout human history, when people have discovered new ways of harnessing features of nature, fire, agriculture, tool making, electricity, it's led to these radical increases in human capability. And associated with each of these, there's usually two forms of revolution. The first is simply using these resources. And usually there's a second revolution wherein you learn to create and then manipulate in a detailed way these resources. An example, say, with agriculture would be first you plant seeds and you grow stuff, then you learn how to manipulate their genes to create specific characteristics for those plants. Quantum computing is this kind of thing. So why would we need unimaginable computing power? Right now, we've built a civilization, and oftentimes this is very underappreciated. We have a civilization of such scale and such complexity and interconnectedness that it's generating problems that transcend human understanding. In every area of human endeavor, there's staggering complexity. I have here some graphical representations of a social network for a single individual. Each one of those points is a little node. It could be someone else you're interacting with, a machine. There's another graph here of the interactions between drugs and gene products, proteins, financial network, stocks, companies, computers, energy distribution networks, and you'll notice a common feature for all of these complex systems on Earth. They have lots of variables, lots of elements interacting in incredibly complex ways, and what this leads to is vast inefficiencies. None of these systems are anywhere near optimized, and it has the potential for vast system crashes. One thing, as a specific example, in financial systems, oftentimes you'll hear after the fact, some financial crashes going on and things changing in the world, and you'll hear these after the fact analyses, and by and large, they're inaccurate. The reason those things can happen is because you have these incredibly complex systems, and the models we have for them are completely inadequate. So don't we have the kind of resources to create really complex models already? We have the internet. So we have people from all over the world interacting to solve problems at scales never before seen in human history. We have massive data centers. That's an example of a Google data center. We're generating data at staggering rates about everything on Earth. We're developing machines that change their own structure with data and learn in ways that humans can, machine learning and neural nets. So the issue is, though, that even with all of that stuff, and even if we were to scale it up by a factor of 10, 100, a billion, they're not enough to solve problems we're going to face going forward, and even at the scales we're at now. Why? There's a branch of computer science called complexity theory. And what complexity theorists do is they look at how the resources you need to solve a problem, say the number of calculations, scales with the size of and complexity of those problems. The line you see on the bottom that says n to the fifth, that shows how our resources can be scaled up to try to solve very large problems. The other line that is blowing up exponentially shows you how trying to analyze large scales, problems of interacting variables, often scales with the problem size. We'll never catch up unless we can access new resources in nature. The kinds of problems I'm talking about, optimizing complex systems, this is often underestimated. A mundane problem like FedEx, trying to figure out the routing strategies for all of their packages and minimize fuel consumption, can't be done on all the supercomputers they have now. Energy distribution networks. systems of stocks and how do you arrange your stocks to minimize risk. Nobody can actually analyze those at scale and get optimal solutions. The simulation of even relatively simple molecules. If you're trying to design a new catalyst, if you're looking at biologically important molecules like HIV protease, you can't analyze the dynamics of those molecules if you had a supercomputer operating for 1 billion years. And most of the problems that underlie truly realizing artificial intelligence at their base are these kinds of optimization problems. So what do? Well, there are resources that we humans have yet to tap into that are vast. At the beginning of the 20th century, there was something called quantum theory. People were looking at the dynamics of atoms and molecules, and they found that those atoms and molecules behave nothing like what you experience at macroscopic scales. Electrons aren't little particles that go around in orbits. They found really bizarre phenomenon. The theory to explain that, called quantum theory, explains everything that we know, other than Einstein's general relativity and gravity. So the structure of matter and radiation and almost everything you experience is explained by this theory. And when this theory allowed for what I call the first quantum revolution. It allowed us to understand why the stars shine. It allowed us to sequence DNA and usher in the age of molecular biology. It ushered in the entire semiconductor revolution with the invention of transistors and semiconductors, lasers, nanotechnology, nuclear energy. All of that was enabled by this original understanding. The interesting thing, though, is that equation down there, the Schrödinger equation, people used it, but they didn't necessarily take seriously what it said about the world. So you see there a picture of what's called Schrödinger's cat, where you have a cat that's both alive and dead at the same time. And you hear about these strange quantum phenomenon. But basically what people did is kind of ignore the strangeness for about 50 years. I called it the shut up and calculate philosophy. They used it to develop all kinds of technology, but they didn't take seriously the strangest effects that this theory predicted was part of our world. What are some of those effects? So here's 3. There's something called superposition. So here you see point A, say an electron is going from point A to B. Your common conception of how an object travels from one place to another is to take a single trajectory across space. Electrons actually take all possible paths simultaneously. And this is very well understood, and we've been doing experiments like this in labs for the last 80 years. So you say, how could that improve problem solving? Imagine that you're at point A, and you have to go through a maze with 1 billion possible paths to escape. If you're a classical you, you're going to try one path, that didn't work, come back, and you could imagine it taking many, many lifetimes to get through 1 billion or never. But what if the same physical you could travel all those paths simultaneously? Electrons, in fact, do this. But there's another quality that you need. If all of these different selves and these parallel streams of reality can talk to each other and collaborate, they could all get out, right? So you have to be able to, coherent evolution is when these paths can talk, so I'll bring that up later. Another effect is quantum tunneling, wherein I can have an object on one side of an impenetrable barrier, and it will disappear and appear on the other side of that wall. That's another way that you could escape and explore domains that would otherwise be forbidden to you as a classical entity. And finally, quantum entanglement, which really bothered Albert Einstein. And I have here a prosaic example. Imagine you had 2 pairs of dice, one in California, one in New York City. You roll them 1,000 times, and each one of the participants sees a set of random results. But if you compare the die rolls 1,000 times out of 1,000 or 1,000,000 out of 1,000,000, they got the same result every time. It's as if the dice know about each other with no physical connection between them whatsoever. And that's how those disparate paths can talk to each other. So what if I could harness these effects in real computing system and explore a vast number of possibilities simultaneously? So when people started thinking about how to engineer systems based on this kind of quantum dynamics, you want to build it out of fundamental elements to make the engineering easier. So there's something called qubits. So bits, what you're all used to, it's a 0 or 1, basically a switch that can be on or off. But what if I could build a device that could be in two possibilities simultaneously and then concatenate them into an array? So here you see each one of those little rings represents some object that can be in two states at once. The next object's in two states, so when you concatenate them, you get 4 possibilities, and then 8, 16, 32, etc. And the number of possibilities you could realize in a system of such quantum objects blows up exponentially, just like the problem sets that we want to solve as a civilization. People started building systems that could do this out of microscopic constituents in the 80s. And Dave Wineland and the group at NIST won the Nobel Prize, I think, last year for exactly this. You can see there a cartoon. There's a number of atoms. They're trapped in, it's a cartoon of some atoms trapped in a vacuum in an electromagnetic trap. You can put them into these strange states where each object's in two states at once, concatenate them, and have them realize these possibilities. What set the field on fire was in 1994, a computer scientist named Peter Shor at Bell Labs said, okay, we've seen that the quantum theory predicts this multiplicity in our universe. We've seen that people are starting to build experimental realizations that demonstrate these effects. So he wrote an algorithm assuming people would continue to scale these effects up and demonstrated that you could factor a large number into its prime constituents, a 200-digit number, instead of 3 billion years on massive classical computers, 1 second on this quantum computer. Why did that excite everybody? Because being able to factor large numbers means you can break our most secure form of encryption called RSA. So this is when everybody went crazy, NSA, DOD, you could undermine our civilization with these things. And to put it the way David Deutsch, the progenitor of this field, quantum computation will be the first technology that allows a useful task to be formed in collaboration between parallel universes. So how cool is that? Now, there's an interesting quandary though. Why is it if the universe at this microscopic scale behaves that way and you're built out of those constituents, you're not doing that? This also wasn't understood until the 80s and 90s, and it's a process called decoherence. So you can see a little picture there where you have the quantum dynamics where there's the alive and dead cat and everything's kind of fuzzy and living out multiple possibilities, and then our classical reality. And where's the border, and why is there one? Well, there you see a strip of film representing two realities, and when the two pieces of film are stuck together, we call that coherent evolution. They can talk to each other. What happens is, for macroscopic systems like this microphone, the environment that's interacting with this microphone, the air molecules bounding into it, the sound waves, the fact that I'm holding it with my hand and the vibrations, all those interactions, when you put it into those equations, show that the interactions with the environments will pull the parallel streams apart so that they can't collaborate anymore, and therefore you lose the power of those disparate experiences. So what does that immediately make you understand? If I could get rid of the environmental influences that pull the streams apart, I might be able to see quantum mechanics at macroscopic scales in systems I can engineer. That was achieved in 2000. So they took a ring of metal, specifically a superconductor. They put it in an ultra-high vacuum at ultra-low temperatures, radiation shield it and magnetic shield it, and if you get it just right, they were able to put this in a state where an electrical current, all the electrical current would travel clockwise, and all the electrical current traveled counterclockwise simultaneously. And this was done at SUNY State University in New York in 2000. And on the New York Times article, it said, Schrodinger's cat lives, because this is a macroscopic object doing two mutually exclusive things simultaneously. The other thing about this object that's so nice is you can build qubits out of it. So current going one way gives you a little magnetic field pointing up. Current going the other way gives you magnetic field pointing down, and I can use those to encode a 0 and 1. And if I can put it into this funny quantum state, it's that fundamental object that I can build multiple possibilities of at scale. So up until now, the US government, after the Shor's algorithm, for the last 20 years has spent a few $1 billion mainly on microscopic systems like ion traps, photonic-based stuff, optical lattices. The problem is there's no known way to scale those systems up. But that little ring that I showed you is macroscopic, and you can make it by etching a metal like you do in a standard CMOS process. And my company, D-Wave, is doing exactly that. We've built a scalable technology based on those kinds of rings, concatenated together with a complex control infrastructure made out of superconducting circuits. And we also picked a model of quantum computing most people weren't considering that was developed at MIT that's much less sensitive to that environmental pulling apart of the parallel streams. So the other thing is, when looking at all the activity in the world, there aren't so many Bell Labs anymore. And I think most of the innovation is going on in small companies. I used to run a DARPA project, and then before that I was in a big company doing quantum computing. And I said, look, we're going to go out, form a small company, just like Celera Genomics, doing the human genome sequence, SpaceX, commercial space travel. There are small companies even working on fusion reactors now. You get the best and brightest people together. You're lean, you're fast, you're bureaucracy-free, and you'll get the best people, and you're willing to take big risks. So we built a company. We began real technology development in 2005. We have visionary investors who aren't just looking for a quick buck, but truly want to change the world, like Draper Fisher Jurvetson, Goldman Sachs, US government, Jeff Bezos, and others. We've developed these superconducting quantum processors. We have about 130 employees, raised about 170 million. We have more patents in this space than most other companies combined. And we have this unique infrastructure where we do everything, allowing us to innovate at every step in the process. We design these quantum processors, we build them, test them, we develop the quantum theoretical frameworks, and we're developing applications. Now, forward-looking companies know that the quantum age is upon us. And if you want to be a leader in the field, you can't ignore this anymore. It used to be thought that these quantum technologies were 50 or 100 years out. Now we're seeing groups from all over the world pursuing this because it's the game of the century. NASA and Google bought one of our systems. It's located at NASA Ames. We have Lockheed and USC Information Science Institute that now have early generations of our quantum processors, are doing basic physics as well as developing applications for a whole range of applications. This is a picture of a unit cell of a chip. So there you see the little object that can have spin up or spin down. You can see the real object is this extended, that red line is circling the real qubit, which is a big, long, skinny guy. Where they cross, they interact. And I can build networks of these qubits where that looks rather like a neural net. And you can see on the bottom the actual topology of the chip. And it looks kind of like those graphs for those complex problems we want to solve. That's an actual chip bonded up. You can see the little guy with all the little squares. That's 512 quantum objects. And that means if you put each one of them into a superposition state, that can go into 2 to the 500th configurations of spins up and down simultaneously. The way that our processor works is that you can see there I have spins with their interactions between them, which are those loops. And what happens is we can encode into our chip, we can create what's called an energy landscape that represents the space of all possibilities that we want to explore. The lowest valley of this energy landscape, of this interacting spin system, is the answer to your problem. You know, how do I arrange the elements of these complex network to optimize some feature that I'm interested in? And now if you were a classical spin system, people have built, you know, you can have spin systems that are classical. If I was in that landscape, so each point of that landscape is a different configuration, I'd be somewhere, so you're in that landscape, and I start walking around. And you could see if you had 2 to the 500th hills and valleys, how long it would take you to explore that landscape. If you're behaving quantum mechanically, it would be as if you had a vast army going out in all directions, and not only can they explore simultaneously that landscape, but they can talk to each other through this quantum entanglement where they know what the other one's experiencing. Now, in order to have those quantum effects continue to manifest themselves, if I don't want those parallel streams to stop talking to each other, I have to create a rather exotic environment where there aren't these environmental disturbances from the outside pulling the streams apart. So you can see the chip here. It's in special materials, oxygen-free copper, gold-plated. You can see the chip then has a radiation shield on it. If I want to, I have to tell it what to do. So this is a bit of a quandary, because in telling it to do, I have to interact with it. But does that pull the streams apart? Not if you do it right. So when you talk to quantum systems, you talk really softly. That then goes into something called a dilution refrigerator, which uses some exotic quantum fluids. You can see the chip there in its radiation shield with the lines going to room temperature control electronics. All of that infrastructure is to take the chip down to 20 thousandths of a degree above the theoretical lowest temperature in nature. Then that goes into a big Faraday cage, that big box on the outside. It's not because all the computing elements that are that big, but for early generations, we fit 4 physicists inside there to play with it as necessary. And it's 150 times colder than interstellar space, with the magnetic field shielding 50,000 times less than the Earth's field, and excludes all radio frequencies and electromagnetic radiation from the big black box. Okay, so imagine you want to look through a search space. So one of the most powerful cancer drugs in history, called Gleevec, there was a realization, one of the first rationally designed drugs. A lot of drug design is trial and error. In this case, there was a group that looked at that. There was a cell regulatory molecule. It's an enzyme that regulates the rate at which cells divide. And they determined the detailed structure of this so-called kinase molecule. And they found that, say in leukemia, for a certain kind of genetic mutation, it would change the shape of this key regulatory molecule. And when you change the shape of the molecule, you would get unregulated cell growth, which is cancer. And the way they solved this was by looking through you could look through a vast database of available synthetic molecules. Maybe there's 13 million of them. And you have to find which pattern of that large database will fit lock and key into the active area of that aberrant regulatory molecule and shut it down. When people found the molecule that fit there, and you had that mutation, it was almost 100% efficacy. But searching through large numbers of complex patterns is a very computationally intense task. And it's just like there, you can see there's a landscape where all the hills and valleys represent different structure matches. And if you could do that much faster, you could enable things like drug discovery and better treatments for disease. Another example would be neural net optimization. So right now we have all this big complex data. People want to make systems that in an autonomous way can do image recognition, speech recognition, machine autonomy. If I have a little robot running around Mars making its own autonomous decisions or autonomous cars. And we'd also like to look at data and make discoveries and see patterns that no human ever would, because we have intuitions for something like faces, but we don't have intuitions for complex genomic data and what it means. So everybody's trying to get insight out of big data. One way that they do that is they build these complex neural nets. So people are now building either abstractions of human neural nets or actual hardware. You hear about neuromorphics. And they build systems where you have these little dots are like neurons in your brain. Those interconnections are like the synapses. And the question is, we don't know how to program something to understand speech. We don't know how your brain does that. What we do know how to do is how to have that network learn from examples and change its own structure until it becomes the kind of thing that can understand speech. But the learning algorithms to find out of all the possible combinations of how to turn the knobs on all those interconnections are horrendous. And as you make larger and larger neural nets, the number of calculations explodes exponentially. So again, if you could search through a large search space of possible interconnections to optimize those neural nets, you can enable a lot of AI that people are looking at now and get more meaning out of large data sets. So here's a couple of forward-looking companies and research centers. That's the computer, our quantum processor at the Google NASA Ames Artificial Intelligence Center. We also have, those are the guys at Lockheed and ISI, USC. There's whole teams now of physicists that are looking at all the quantum dynamics of our processors, as well as people working on apps in these early generations, looking at pattern recognition, protein folding, bioinformatics. And where are we at? So at 500 qubits, these are early days. But we have by far the largest quantum processors ever built, and they also have a scalable infrastructure that we know how to scale up with standard CMOS processing and macroscopic quantum dynamics in qubits. So we took some off-the-shelf optimization solvers to look over complex landscapes, CPLEX, and saw where we could, we would beat it by 100,000 times, which was very exciting, meaning the thing that we built is no toy. It's a very powerful. But to be fair, that optimization solver is a general purpose solver, and ours was more specific. So research groups got together saying, let's get some specialized hardware with specialized algorithms and go head to head with these early generations of D-Wave. And in that case, they're taking these processors, to get some perspective, that took 60 years and $1 trillion to build and 50 years of history, and we're now matching that state of the art and sometimes exceeding. So I believe we're at a tipping point, and that in the next few years, we could have something that could exceed everything on Earth for specific applications. We have a very high rate of discovery and innovation. Between our last two processor generations, in 2 years, we didn't have a factor of 2. We had a factor of 300,000 in performance gain as we scaled up our qubits and infrastructure. And we've been on a Moore's Law-like trajectory since 2002. So very rapid rate of innovation. And to give you perspective, I think we're at a point in human history. It's not just quantum computing. There's also quantum communications, where people are creating these secure keys. There's quantum teleportation, wherein you can have information at one location that disappears, appears at a remote location without a signal being sent. They're finding coherent quantum dynamics that underlie the efficiency of photosynthesis in plants. We're coming into a new age, and for industries, forward-looking industries, I believe that they need to pay attention to this very acutely. And I'll show you a quote by the physicist whose books I read as a child that encouraged me to go into physics, Paul Davies. The 19th century was known as the machine age. The 20th century will go down in history as the information age, and I believe the 21st century will be the quantum age. I believe that. So thanks for your attention.
Eric, thank you. That was... we have time if you're willing to take a couple questions.
Yeah, sure.
Okay. Right there, I'll come back to you.
Thank you. Do we have the 512 qubits? Are we able to entangle all of them together to create one superposition of all of them?
Yeah. So this is a good question. So one of the questions that people in the field have asked. So most people are building small-scale systems. So you can have 5 qubits, 6 qubits, 7. And when you have a small number of qubits, if you look at the total number of possibilities, it's possible to completely characterize those quantum states, right? Because I got 32 of them or 64. And you can do, but the number of measurements you have to do to confirm that you're fully quantum mechanical blows up exponentially. So what we've done in our processor, there's nobody on Earth who knows how to confirm, if I had 500 qubits, that I have 500 qubit entanglement, because you can't generate the predictions. So if you have 500 qubits and you say, okay, if I have 500 qubits, write the Schrodinger equation and calculate what you should see. You can't do that, because if I could, what do I need the quantum computer for? So instead what we do is, when we build our processor, we look at subsections of the processor. And so recently we had a paper out where we showed world record entanglement, the largest scale objects, patches of that processor. And you can look anywhere and you'll see that entanglement. But there's no way to say, are all 500 qubits entangled, because you can't even generate the predictions. So it's a tough problem for anybody who starts getting to scale. Yeah. Yeah.
Yeah, you were mentioning superconducting controller associated with managing these qubits.
Yes.
How do you achieve the device?
How do we achieve an active device? Oh, so one of the nice things is, before I went to D-Wave, I was at a place called TRW. There's a mature circuit technology in superconducting electronics called single flux quantum electronics. So we're not using CMOS circuits at low temperature. There's a device called a Josephson junction, and it will send these picosecond pulses. So the way our circuits work, we have all these rings, and you have to put magnetic field in them or flux to control them. So there's a technology called single flux quantum logic where you can have pulses of quantized magnetic field that travel at the speed of light ballistically down a line with no energy dissipation, and we have a routing system on chip. If you're qubit number 37, where I can have a piece of magnetic flux travel at the speed of light, make a left turn, and plop in the ring that I want. And the only components to that process is actually quite a bit simpler than CMOS. A Josephson junction's a glorified capacitor, metal insulator metal, and it uses that tunneling phenomenon I talked about. And then you have a lot of superconducting lines, which is niobium or aluminum wires, and dielectrics, and that's it. And so we hired the entire design team, and everybody from TRW came over to DWIP. Anything else? Yeah.
Yeah, hi. So quantum computing is just one method of a few other methods being researched to kind of bring about the next generation of computers. So I've heard of carbon nanotubes, being developed at Stanford.
Yep.
And I think there's wave computing, right, where the electrons are spinning and you calculate them based on their wave spin or something. So it seems to me that these three kind of different approaches are trying to achieve the same thing, really. So where would you rank them? And what are your comments on these methods?
Yeah, so it's a really good question, and there's a straightforward answer to that. If you build a system, so you could take carbon nanotubes. So I could make things smaller. I could make them faster. I could make them less energy dissipative. I could make them, interconnected neuromorphics like human brains. If you don't harness quantum dynamics, you will never solve problems that blow up exponentially like that, because the physics. If you have a device that works on classical physics, it doesn't matter what it is. It will never match a system that uses quantum dynamics. I mean, early in the 80s, Richard Feynman, the famous theoretical physicist, he had this realization way back when. He said, look, if I take a system of qubits, right, quantum objects that can be in two states at once, and concatenate them, the number, you'd have to write 2 to the n numbers down, right, to specify its state. So it doesn't matter how many classical computers you have, they'll never scale like 2 to the n. So if I take 2 processors, okay, I get a linear increase in speed at best. So the thing about quantum dynamics, the size of the multiplicity of quantum systems is fundamental in nature. So any other approach, it doesn't matter what it is. If it's classical, it will never achieve those kinds of scales. Say again? Oh, how many years until you... Yeah. Oh, how many years for a quantum system to exceed everything? Or even the things that are evolving now? Yeah, so it's a complex question because, of course, when you build these systems, it's really hard. They're very complex. It's early days. But we're already seeing kind of rivaling very powerful systems that took a long time to build. And, we think, I kind of think in the next 3 to 5 years, something on that time frame, we could have something that at least for some set of applications or problems might exceed anything you can do classically, independent of the approach. But it's true that there's the processor that we're building that builds these landscapes and looks through them in a certain way, it's not completely universal for all computation. So there will be, it's specifically designed for those optimization problems, and there's whole sets of other problems that could leverage other stuff that's going on. And it's not like quantum computers are going to replace all computing, because there's a lot of stuff that classical computers are perfectly fine for, and they still want to make them more energy efficient and better for learning tasks and all that. So that's all going on, right? And of course, there's always risks in a project this ambitious and crazy. But I think that ultimately, people used to think it was 100 years off, and nobody believes that anymore. I think certainly in the coming decade, we'll see systems that are impossible to rival with anything that doesn't harness quantum dynamics.
Erick, thank you very much. We'll leave it there.
Sure.